So I'm going to present my work on a question regarding prime numbers, and more precisely their digits. So throughout my talk, g will be an integer larger than or equal to 2. It will be the base in which we will work. So we know that any non-negative integer k can be written in base g in this way, with its digits. So epsilon j of k is the digit of k at the position j. So on the one hand, we can represent an integer with its digits in base g, and on the other hand, we have its multiplicative representation as a product of prime factors. And the study of the connections between these two representations, and also the study of their independence, leads to many important and interesting problems. Among these problems, there is the following: are the digits of primes random? So there is a famous conjecture on this topic by Gelfand in 1968, which says that the sum of digits of primes is well distributed in arithmetic progressions. So for example, if you pick a prime at random among primes which are less than x, then the probability that its sum of digits is even and the probability that its sum of digits is odd are asymptotically the same, so 1/2. Fourier and Mauduit obtained results in this direction for integers which have at most 2 prime factors, and Dartige and Tenenbaum for integers which have exactly all prime factors. And finally, Mauduit and Riva proved the conjecture in a paper published in 2010. In another direction, Maynard also contributed to the study of the pseudo-randomness of the digits of primes when he studied primes with missing digits and proved that there are infinitely many primes with no digit 9 in base 10. Okay, another very interesting topic about prime numbers is the study of prime numbers in sparse sets. So a sparse set is a set such that the number of elements in the set which are less than x is a little o of x. So for instance, the integers of the form 2 to the n minus 1 form a sparse set, and the existence of infinitely many primes of this form, called Mersenne primes, is an open question. Also for primes of the form n squared plus 1. But we know that there are infinitely many primes of the form m cubed plus 2n cubed, or also of the form m squared plus n to the 4. The integers of the form integer part of n to the c, where c is a real number strictly larger than 1, form also a sparse set. And Riva and Sergos obtained an asymptotic formula for the number of primes of this form when c is less than 1.16. And when he studied primes with missing digits, Maynard also actually studied primes in sparse sets, because, for instance, the set of integers with no digit 9 in base 10 is a sparse set. Okay, so now we'll focus on the following problem. So we'll consider integers k strictly less than g to the n, non-negative. So they are represented with the first n digits from the position 0 to the position n minus 1. And for some positions, say here, 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 and here, we will preassign or also prescribe the value of the digits at these positions. Elsewhere, there is no restriction. And what we want to do is to count, to estimate the number of primes which have these digits at these positions. So more precisely, we consider a set A of integers between 0 and n minus 1. This is the set of the positions. And for each position, we consider a value for the digit, dj. And we want to estimate the number of primes less than g to the n, such that for any position in this set, the digit at this position is equal to dj. We will just assume that 0 is in A, so that means the rightmost digit is preassigned. And actually, this is not a restriction, because if you know how to estimate this when the rightmost digit is preassigned, then if the rightmost digit is not preassigned, it suffices for each value of this digit to estimate the number of primes which have these digits and also this one preassigned to this value. And then we sum over all the possible values. And we will also assume that this digit is co-prime to the base, because otherwise this problem is not interesting. There is at most one prime in this set. Okay, we would like to be able to do this with a set A which is as large as possible. Why? Because we are trying to estimate the number of primes in the set of integers k less than g to the n, such that for any position j in A, the digit of k at this position is equal to dj. And what's the number of integers in this set? So for each position in the set A, the digit has to be equal to dj, but for the other positions, there are g possible values. So this is g to the power of the number of digits which are not preassigned, which is n minus the cardinality of the set A. So the larger the set A is, the smaller the set in which we are looking for primes is. And if the number of elements in the set A tends to infinity, as n tends to infinity, then the set in which we are looking for primes is a sparse set. We would like to be able to do this without any restriction on the set A itself, and also no restriction on the digits. So that means we would like to be able to preassign digits anywhere and at any value, except for this one. So before going further, what's the expected estimate for this, under this hypothesis? So one way to answer is to consider the set E1 of primes less than g to the n, such that the rightmost digit of p is equal to d0, and the set E2 of integers k less than g to the n, such that for any j in A, which is not 0, the digit of k at this position is equal to dj. So with these two notations, what we want to estimate is the cardinality of their intersection. Okay, so first, what's the number of elements in E1? So the elements of E1 are the primes which are congruent to D0 modulo the base. So by the theorem of de Laval-Poussin for primes in arithmetic progressions, this is g to the n over phi g log g to the n. Then for E2, so by the same argument as before, this is g to the power n minus the cardinality of A plus 1. And, okay, so now we pick an integer k, strictly less than g to the n, at random, and we look at the two events. K belongs to E1, and k belongs to E2. So we expect these two events to be independent. So now, if we look at the probability that K belongs to E1 and E2, it should be the product of the probabilities. So it should be the probability that K is in E1, which is this divided by G to the n. So 1 over pi G log G to the n times the probability that K is in E2, which is G to the power minus the coordinates of A plus 1. Okay, so now the number of elements in this intersection should be this probability times G to the n. And this is exactly this. So this is the expected value. Okay, so this question has already been studied by many authors, which were able to preassign more and more digits, and so to study primes in sets which are sparser and sparser. Bourgain obtained an asymptotic formula in base 2 when the number of preassigned digits is at most n over log n to the power 4/7. And 2 years later, he made an impressive breakthrough by improving his own result and by proving that we can actually preassign a positive proportion of the digits in base 2. So more precisely, he proved that there is an absolute constant C, strictly positive, which is not explicit in his paper, such that if the number of preassigned digits is less than Cn, then we have this asymptotic formula for the sum of the lambda of k along integers k which have these digits. So here lambda is the von Mangold function. So this sum here essentially counts the primes which have these digits with a weight log p. Okay, so after this result of Bourgain, it would be interesting to provide an explicit admissible value for the proportion C in his result, which is as large as possible because we want to be able to preassign many digits, a lot of digits. Then can we generalize this result in any base? If yes, can we still provide an explicit admissible value for the proportion? And also, we would like to adapt, develop, complete, and clarify some arguments in his paper for which there are difficulties. Sometimes there are difficulties which are not only due to a lack of detail. So I studied these questions, and we prove that in any base, there is an explicit C0, which depends on the base, such that if C is strictly less than C0, if the number of preassigned digits is less than Cn, then we have this asymptotic formula for the sum of the lambda of k along integers k, which have the good digits. So this generalizes Bourgain's result in any base. And then, essentially, by a partial summation, we obtain an asymptotic formula for the number of primes, which have the good digits. So here, this is the expected value. And we just assume these two hypotheses. So we just assume that n minus 1 is in A, so we preassign this position, this digit, and its value is not 0. So these two conditions are quite natural, and we know that we can't just remove them. Okay, so here are some explicit values for the proportion.
Can I ask you a question? In the last slide, your term is like log, it's like the power, small power of log x, yes?
Yes.
Okay, thank you.
Yeah.
That was my question.
Okay, so in base 2, we can preassign 2/1000 of the digits. In base 3, 3/1000. In base 10, almost 5/1000. There are some bases for which we obtain a smaller C0. For instance, if the base is of the form 2 times the big power of 3, But if G runs through prime powers, then C0 is increasing and stands to a bit more than 9 thousandths. Okay, so now I'm going to give you some details about the proof. So I denote by F the indicator function of the integers which have the good digits. And capital N will be G to the N. So with these two notations, what we want to do is to estimate this sum here. So the sum over OK less than capital N of lambda of K, F of K. To do this, we use the circle method, which consists in writing the sum we want to estimate as an integral between 0 and 1 of here a product of two sums, S alpha, sum of the lambda of K, E of K alpha, so I use the notation E of X, which is exponential of 2I pi X. And or alpha, which is the sum of the F of K, E of K alpha. So this equality here just follows from the fact that the integral between 0 and 1 of E of an integer m alpha d alpha is 1 if m is 0 and 0 otherwise. Okay, so in the sum S alpha, we have the information about primes, because we have the von Morgan function here. And in our alpha, we have the information about the digits with the function f. Okay, and we know that S alpha can be large only when alpha is close to a rational with a small denominator. We say that alpha is in a major arc. So I'm going to define more precisely the major arcs after. And for our alpha, it depends on the digital conditions. So we expect the integral over the major arcs to provide the main term in our asymptotic formula for this at the end. And the integral over the minor arcs should just provide an error term. Okay, so before defining the major arcs, minor arcs, and study the contribution, I just want to say a few words about the Fourier transform of the function f. So I denote by this Fourier transform by capital F. It is defined by this equality. So capital F of lambda is this exponential sum. And if we multiply by capital N, this is exactly this sum here, or of lambda, which appears in the integral we want to estimate. So the properties of this function are very important. And okay, for most problems regarding digits, the function in which there's information about the digits can be written as a product, and one tries to take advantage of this product. And here again, we can write capital F as a product. So how? We just write k here in base g. So f here is the indicator function of the integers which have the good digits. So k, when we write it in base g, so for each position in the set A, so for each preassigned digit, the value of this digit is dj, okay? And for the others, there is no restriction. So I denote by A bar the set of positions which are not in the set A. So here we have sum over j in A bar of, say, epsilon j, g to the j. And epsilon j here can take any value between 0 and j minus 1. Okay, so now for capital F of lambda, this is 1 over g to the n times the sum over all the possible values for the epsilon j's. So sum over all epsilon j for j in a bar of e minus k epsilon j, gj, k, and lambda. Okay, so now we can rewrite this. Here, this sum does not depend on the digits here, so we obtain 1 over j to the n. We have a product over all j in A of e of minus dj g to the power j lambda. And then we obtain the product over all j in A bar of an exponential sum, the sum over all epsilon j between 0 and g minus 1 of e of minus epsilon j g to the power j lambda. Okay, so capital F can be written in a product in this way. Okay, so now if we take the absolute value, we obtain 1 over g to the n, this product disappears, and then we have here a product over all positions which are not in the set A, like here, of the absolute value of an exponential sum, and with the notation which is here, so this the absolute value of this is exactly phi g of g to the j lambda. Okay, so this proves this equality. So the absolute value of capital F can be written as a product in this way, where phi g is the absolute value of an exponential sum, which is also actually a quotient of sign. Okay, so now what we need about capital F is very strong upper bounds for first the L1 norm, so the integral between 0 and 1 of the absolute value of capital F, and also very strong upper bounds for some weighted averages of the absolute value of capital F at some rational points. So this seems to be quite difficult because if we look at this product here, this is a product over all positions which are not in the set A, and we don't know anything on the set A itself. We just know that it is not too big. Okay, so I'm going to briefly present what we obtain for the L1 norm here, because this will be crucial to study the contribution of the minor arcs. Okay, so key idea in Borgen's paper was to first study the discrete L1 norm, and then to deduce an upper bound for the continuous L1 norm. So the continuous L1 norm is this, and what I call the discrete L1 norm is this sum here. So if we use this formula here, we can prove that this discrete L1 norm is bounded by this. So here psi depends on the base and also on rho, which is the proportion of the digits we preassign. And what is important is that when rho tends to 0, psi tends to 0. So if the proportion of digits we preassign is very small, then psi will be very close to 0. And so this upper bound here is very good. If we compare with the trivial upper bound, which is here, we obtain psi instead of 1. So when xi is very close to 0, this is much better. Okay, so this is for what we obtained for the discrete L1 norm. And now for the continuous L1 norm, we first prove this inequality here, which allows us to bound the continuous L1 norm by using the discrete L1 norm. And actually, this inequality just follows from the orthogonality of additive characters. And now, so together with this upper bound, we obtain a very good upper bound for this L1 norm. Okay, so now I define the major and minor arcs. So we consider two parameters, B1 and B, which are both small powers of capital N, and B1 will be much smaller than B. We first define the major arc, M of QA. This is a small interval around the rational A over Q, modulo 1. And so its size depends on the parameter B. And then the major arcs are the union of all these major arcs around rationals A over Q with A and Q coprime and Q less than the parameter B1. And then the minor arcs are the complement of the major arcs in 0, 1. In Borgen's paper, the parameter B1 is not introduced. And with our notations, this corresponds to taking B1 equal to B. And we will see later that there is a localization argument which does not seem to work in all cases when B1 is too close to B. So this is the reason why we introduced this parameter, B1, and we choose B1, which is much smaller than B. So our definition of the major arcs, and so also the minor arcs, is not exactly the same as in Borgen's paper. Okay, so for the minor arcs, we just want to show that their contribution is an admissible error. So we want to bound this integral here over the minor arcs. So to do this, we take the supremum of S of alpha over the minor arcs. We put it outside. And then we extend this integral to the interval 0, 1. And what we obtain is exactly capital N times the L1 norm of capital F. So the L1 norm of capital F appears in a very natural way here. And now we have to show that this is small enough. Okay. To show that S of alpha over the minor arcs is very small, this is classical. We use the classical estimate, which is essentially due to Vaughan. And now we have to bound the L1 norm. We could just say that it is less than the L2 norm and compute the L2 norm. But this is not enough. So we really have to study the L1 norm. So the fact that we have a very good upper bound for this L1 norm allows us to handle the contribution of the minor arcs here. Okay, now for the major arcs. So we have, just by definition, the contribution is equal to this. And the first step is to replace the indicator function of this interval by this smooth function here, where W is well chosen. I'm going to give you more details about this function W. So, of course, this creates an error term, and we have to prove that it is admissible. And we will see that we can choose the function W so that the error term we create is bounded by this integral over the minor arcs. And we have already studied this integral. We know that it is small enough. So the error we create is admissible. Okay, so here is the function W we consider. So its graph is here. So this is a function, it takes value between 0 and 1. It is equal to 1 on minus 1, 1. It has support in minus 2, 2. It is smooth, and its Fourier transform, which is drawn here, is very small at infinity because of this. And this last property will be essential. So now, with this function W, why is the error we create here bounded by this? So we can just draw a picture to understand. So I just represent two major arcs. So the first one around A over Q, the second one around A prime over Q prime. So at the beginning, we have the indicator function of those major arcs. And so we replace this indicator function by a function like this. So the error we create corresponds to these intervals. But here, we are in the minor arcs. So this is the reason why the error we create is bounded by this integral over the minor arcs. So of course, we have to choose the parameters which are used to define the major arcs so that there is enough space here between two consecutive major arcs. Because we don't want, for instance, this interval to intersect this major arc. Okay. So now, second step, we switch to multiplicative characters. So in the integral we want to estimate, we have this product of two sums. And we replace S of alpha by this quantity here. We can do this up to an admissible error term. So now we have a sum over all characters chi mod q. And we expect the contribution of the principal characters to provide the main term in our asymptotic formula at the end. And the non-principal characters should just provide an error term. So we begin with the principal characters. Their contribution is exactly given by this quantity here. So we have a sum over OQ less than B1 square free, a sum over K2 with the function f here, the indicator function of the integers which have the good digits. And then mu is the Mobius function, and then a sum over K1 with lambda of K1 here. So in this sum, we have information about primes. We want an asymptotic formula for this. Okay. We saw that the Fourier transform of W is very small at infinity. So if K1 is too far from K2, the contribution should be negligible. So more precisely, the size of Fourier transform of W allows us to restrict the summation over K1 by adding this condition here. And since Q is less than B1, the distance between K1 and K2 is less than this. And since we choose B1 and B such that B1 is much smaller than B, now K1 runs through a short interval around K2. And so in Brogan's paper, since B1 is equal to B, this argument does not allow us to restrict the summation over K1, because if B1 is equal to B, this is very big here. So this is the reason why we introduced the parameter B1 and we choose B1 and B such that B1 is much smaller than B. Okay, so now the contribution of the principal characters is given by this. So this is exactly the same as before, but now K1 runs through a short interval around K2. The first step to obtain an asymptotic formula for this is to replace lambda of K1 by 1. How can we do this? We use a partial summation and then an estimate for primes in short intervals. And so now we can forget this lambda of K1. And we have just this sum here. And since again, W hat is very small at infinity. We can extend the summation over K1 to K1 in Z, and then compute the sum. So this is the sum, and by the Poisson summation formula and the properties of W, we obtain just 1. So up to an admissible error, this sum here is equal to 1. So now we have to study this sum over K2, over Q and K2. Okay, which is here. To do this, we use a strong upper bound for some weighted average of the Fourier transform of f at some rational points, an upper bound for this average. And we obtain that this double sum is equal to this, plus an error term. So this is the main term in our asymptotic formula. This will be the main term in our asymptotic formula at the end. And also the calculations allows us to know which major arc contribute in this main term. And these major arcs are the major arcs around rationals A over Q, where Q is a square-free divisor of the base. Now for the non-principal characters. So we use again the localization argument as for the principal characters. And then we subdivide the characters into two classes depending on the zeros of the corresponding L function. So if the L function associated to our character has no zero close to 1, then we say that this character is good. And for such characters, the idea is to use a similar method as for the non-principal characters. So more precisely, we will again take advantage of the summation over K1 as for the principal characters. Here, we took advantage of this sum. So why this? For the principal characters, we used an estimate for primes in short intervals, which comes from the explicit formula for psi, a zero-free region for zeta, and a zero density estimate. And now, since we know that there is no zero close to 1, we expect to be able to adapt this idea. So we will use the explicit formula for psi of x and chi, and again, no, not again, but a zero density estimate in this case. Okay, and now for the characters for which the corresponding L function has a zero close to sigma equal to 1, we don't expect to be able to take advantage of this summation over K1. So we try to take advantage of the summation over K2. And now, so in this summation over K2, we have the function f, and we also have a character. So we are led to study correlations of f with characters. And to do this, we use, again, an upper bound for the Fourier transform of f at rational points. And we also need an improved zero-free region for spatial moduli, which is essentially due to Ibanez. Okay, so finally, which is a good choice of the parameters, B1 and B. And if C is small enough, we obtain this asymptotic formula for the sum of the lambda of k, f of k. So the circle method, together with the fact that we have a very good control for the L1 norm of the Fourier transform, allows us to deal with a binary problem, which is usually out of reach for prime numbers. So this generalizes Borgen's result in any base. We adapt, replace, or complete several arguments in Borgen's proof. Sometimes we had to proceed in a different way. We gave explicit values for the proportion of digits this method allows us to preassign. And we also had to solve new difficulties when the base is not a prime number. Thank you.
Any question? Can you?
So what about counting primes with preassigned digits but in short intervals? So probably a circle method should still work to a certain extent, but past that extent probably we should use other techniques like Maynard's sieve. But have you already thought to it?
I have to think about this, but what I can say that if the digits are preassigned on the left, so you just preassign the block of digits on the left, then this is already the problem of estimating primes in short intervals. So there's a link, but I don't know.
Okay, thank you.
Any other?
So in the previous slide, I guess that if you assume the GRH, it simplifies a lot the argument. Yeah,
Yeah, there is
sure.
no.
Does it improve the estimate in any way?
Sorry?
So it assuming the GRH will simplify the argument, but does it improve the estimate or not at all?
This improves the proportion of the digits we can preassign. Yes. Yeah. In base 2 under GRH. Under GRH, we can preassign 1.6% of the digits. And the C0 we obtain under GRH is an increasing function now, and it tends to a bit more than 7%.
And the error term?
I think the error term is still of this one. Yeah. Because I wanted to improve the proportion. So I just wanted the error term to be like this.
Yeah. Any other question? Oh.
Have you looked at other sequences than primes?
Not yet. Not yet.
Thank you.
Yeah. You another question, right?
So I was just wondering about the next slide, I think slide 9, where we have you have C0 of G times 1,000. Why is it that the second last value is substantially smaller?
This one?
Yeah.
Yes, because the proportion C0 we obtain satisfies this inequality. It is less than log P1 gamma 1 over 8 log G. So G is the base, and P1 to the power gamma 1 is when we write G into a product of prime factors. So let's say P1 to the power gamma 1 times Ps to the power gamma s. So P1 to the power gamma 1 is the smallest of this term. So we have this inequality, and when the base is of the form 2 times a very big power of 3, so G is very big, but this is just log of 2. So this is why C0 is very small. Yeah.
So, any other further question? If there is no, please give big hand to the speaker.